Chemistry is the study of matter, the 118 elements that make up everything we see. It is also the study of change, as atoms form bonds to create compounds, and compounds react with other compounds to make new substances from old. It is the bridge between the other sciences, holding everything together. You are about to enter a world so small that gravity no longer matters, and we must turn to other forces to explain its existence. This is chemistry.
Part 4. Ionic and covalent bonds. In Part 3, we covered how electrons are arranged in an atom. This part will explain how electrons are shared between atoms. Electronegativity is a measure of how strongly elements attract electrons in bonds. It ranks all of the elements in relation to each other. Francium has the lowest electronegativity at 0.7, while fluorine has the highest at 4.0. When two atoms with the same electronegativity bond, they share electrons evenly. This is the case with nitrogen, oxygen, and the halogens, which, as you may recall from last video, are diatomic molecules. Because the two atoms share electrons, they form a covalent bond. Since they share the electrons equally, the bond is nonpolar. If two atoms have slightly different electronegativities, a polar covalent bond is formed. Here, the electrons are still shared, though unevenly. The electron is more likely to be found around the atom with the greater electronegativity. If the electronegativity difference is great enough, an ionic bond is formed, where the most electronegative atom steals the electrons from the least electronegative atom. In general, covalent bonds exist between nonmetals, whereas ionic bonds exist between a metal and a nonmetal. One way to determine this is to look at electronegativity differences. If there is no electronegativity difference, we have a nonpolar covalent bond. And a difference up to around 2 gives a polar covalent bond. Differences greater than 2 make an ionic bond. Most bonds are not perfectly ionic or covalent, but rather display properties of both. The greater the electronegativity difference, the more ionic the character of the bond. Covalent and ionic compounds have different characteristics that can be used to determine bond type. Covalent compounds typically have a lower melting point and boiling point than ionic compounds. Ionic compounds can conduct electricity when melted or dissolved in water, whereas covalent compounds do not. More ionic compounds than covalent compounds dissolve in water, while more covalent compounds than ionic compounds dissolve in nonpolar substances, such as oil. Ionic compounds are named with the cation, usually the metal, first, followed by the anion, or usually the nonmetal. The end of the nonmetal is replaced with "ide". Examples include sodium chloride and aluminum oxide. Some elements, particularly transition metals, lose different numbers of electrons. In this case, the charge on the ion is expressed in Roman numerals and placed in parentheses after the metal. Examples include cobalt-2 chloride and iron-3 oxide. Covalent compounds are named in a similar way. The least electronegative atom is named first, followed by the most electronegative atom. However, the number of atoms of each type is also specified by a prefix before each atom is named. Examples include dinitrogen monoxide and disulfur decafluoride. However, if the atom named first only occurs once in the compound, it does not have a prefix. Examples of this are carbon dioxide, nitrogen monoxide, and sulfur hexafluoride. Another note, ionic compounds and some covalent compounds exist as very large molecules, so we instead refer to their empirical formula. That is, the number of atoms is reduced to the smallest whole number ratio. Silicon dioxide is an example of this. Up to this point, we have talked about monatomic ions, those ions made of only one atom. It is also common to see multiple covalently bonded atoms that form an ion overall. These are called polyatomic ions. Here is a list of some of the most common ones. We will revisit polyatomic ions when we get to aqueous reactions. Thank you for watching. This is chemistry. The next part will cover chemical reactions, and yes, this is where fire gets involved.